Good morning, class. Hope you had a good weekend. Got a big week ahead of us. So, you know what Wednesday is, right? Your exam 3 is this Wednesday. So, the same deal as before. Multiple choice questions adding up to about 20 points. Quantitative problems adding up to about 30 points. And you will have to, log into Zoom, have the ability to scan or take photographs of the work for the quantitative problems and attach them to the problems when you submit them. All right, nothing new. Same story, just a different day. All right. So today we're gonna start some new material. One other thing. So the lab for this week is posted, and this exam on Wednesday deals exclusively with momentum and the concept of impulse and momentum and impulse. And the lab this week deals with these concepts as well. So kinetic energy is part of the understanding of as part of what you need to understand momentum and impulse. The reason is because some collisions conserve kinetic energy. Elastic collisions conserve kinetic energy. So if you're studying a situation that has an elastic collision, conservation of momentum is accompanied by conservation of kinetic energy. All right. So just because the focus is on momentum and impulse doesn't mean you can forget everything you know about everything else. You still got to remember conservation of energy, of kinetic energy. So Maddie says, will the classroom be open to take it in person? Yes, it will. So that's where I'll be to proctor the exam. I haven't created the sign-up sheet yet. I'll do that right after class. Okay, I'll create a Sign Up Genius sign-up so that you can, if you choose to come to the classroom to take the exam, that will be an option available to you. And I really encourage you to do that. I mean, I don't know, it just seems so much less moving parts to worry about. So if you can make it to the classroom to take the exam, we've had plenty of room in there all semester. Only a handful of students taking that opportunity. All right. So that's what's on tap this week. Oh, okay. I forgot to say what I was going to say. The lab for this week deals with momentum and impulse as well, and different types of collisions, elastic, inelastic. And I believe it would really, really benefit you on the exam on Wednesday if you spent some quality time with that lab before the exam, especially the quiz. All right, so what does that mean? Well, you probably won't be able to complete the quiz entirely until you're done with the lab, but you can look at the quiz and you can answer some of the questions without doing the lab, and I think if you do that, it'll be a good study tool. But everything else, the clicker questions are posted on Sakai. There's review slides posted on Sakai, and all of the recorded lessons on this material are there in the playlist linked to on Sakai, up there on YouTube. All right, so I want to, so we're going to start talking about some new material today, and I don't know what's going on with my computer. This app keeps trying to open. An application keeps trying to open and just bogging everything down. Something changed with my software last week and has created nothing but problems. Maybe there's something running in the background. Let me see. this stuff running. Maybe I'll just try restarting my computer. Sorry about this. Let's see if a restart helps here. But it's freaking out. It's freaking out. So while this is restarting, I got a riddle for you. Okay, I was thinking about this. I don't know what sparked this in my mind, but there's what's that dude's name? There's a famous. Oh, maybe it was because you guys heard that Alex Trebek died, and I was thinking about game shows, I guess. And there's this. There used to be a game show called Let's Make a Deal. And I think the host, it was named Monty Hall or something like that. Monty Hall, yeah, the Monty Hall problem, William. So William, if you know the answer, don't share it. Okay, let's let other people think about this. But this is a cool problem, okay, and it goes something like this. And there is a correct answer. All right. So in the Let's Make a Deal game, there was this game which involved 3 doors. So you had 3 doors, 3 doors, and behind one of the doors was something really desirable, like a car, and behind the other 2 doors were dumb things, like, I don't know, a set of dinner plates, and the third one would be something ridiculous like a chicken. And the idea was, as a contestant, you got to pick one of these doors. Okay, so you pick one of the doors. So say you pick this one, and then Monty would say, "All right, well, let me reveal something that's behind one of the other 2 doors." So he would open up one of the other doors that had one of the gag prizes behind it. So he revealed the dinnerware. Okay, and then there'd be 2 doors left. The door you originally chose, and the other door that's not open. And then you'd have a choice. And your choice was to keep the door that you originally picked, or to switch to the other door. And so there's that strategy. And so the question is, does it make a difference? Is there an actual right answer to this problem? In other words, is there a strategy that maximizes your chances of getting the good prize? Holly says, "Oh, this was solved in the nonfiction book Outliers." I won't spoil it then. Outliers. That sounds like a really cool book. Is that a fairly new book? I've never heard of it before. But it sounds like a really cool book. It sounds like something I would like. So just think on that. And so let me frame it again. Don't look, if you can help yourself, don't look up the answer, but think about it and see if you can figure it out yourself. All right? But here's the situation. There's 3 doors. You pick one, and then Monty reveals one of the gags behind the 2 remaining doors. So maybe, the chicken. Oh, the chicken. Okay. So now there's 2 doors left. The one that you picked first and the other door. And Monty says, "Do you want to keep your first door or do you want to switch?" All right. And one of those things is actually going to give you a higher probability of winning the good thing potentially. So what is the optimal strategy? Published in 2008. Outliers is about geniuses and the 10,000 hour rule and whatnot. I'll have to check that out. Okay, well, I'm back up here. Let me see if I can connect. Oh, it keeps wanting pin number. Connect to my... Okay, and now it's doing that same thing where it it's just really screwed everything up. It like automatically resizes my screen. So I've got to go and change it again. All right, let's try this. So we'll talk about that on Friday after you take the exam on Wednesday and see if you have any ideas about the Monty Hall problem. All right. So here we go. Here's the situation. So what we're going to spend the remainder of our time on this semester is talking about things that rotate. So we can call this rotational mechanics. And what's different about this is, well, the physics that we've learned up to this point can be, let's say, translated into the realm of rotational mechanics, and that's what we're going to spend today doing. We're going to do this a lot of this today. But the type of motion that we've been predominantly concerned with this semester is motion in straight lines. We did talk about uniform circular motion. Okay, so that's a little special case. But we've been talking. We even just now we got finished talking about momentum. But if you look at the title of the chapter, it's called linear momentum. So it's called linear momentum because there's another kind of momentum called rotational or angular momentum. Okay. And all right, so rotational mechanics. Let's set it up this way. Okay, so what we're going to do is let's imagine that there's a little particle that has a mass m, and this particle is attached to maybe I'll draw it solid, a rod that's massless, okay, this massless connector to a pivot point here in the middle, and we'll call that the axis of rotation. I'll label it AR for short. So this mass is going to be free to rotate around in a circle about the axis of rotation. All right, but at any moment in time, if you look at this mass, it's going to have a velocity. Okay. And its path has a radius. We'll call that r. All right. So let's think about how you could quantify. Well, before we do that, let's think about how this thing moves. So this is at some moment in time, a snapshot. And as it rotates, at some time in the future, it's going to be, it's going to have moved somewhere else. Okay? And so, and the arm has moved as well that it's rotating on. And we can talk about the distance that this thing has traveled in terms of, I overwrote my V. Let's erase that. A little arc length. That is, so this yellow thing that I drew here, it's called an arc length, and I won't call it X or Y, I'll call it S, something different. That's way too thick. I'll call it S. It's a distance. It will have units of meters, and that's one way you could quantify how far this point mass has traveled in a given amount of time by specifying the arc length that it traveled. So what's the arc length of one complete revolution? It would be 2 pi r. It's the circumference of its circular path. But there's another way that you could specify how far it's traveled, and that would be in angular terms. You think of this a line, which in this case we're saying it's a hypothetical rigid thing that connects this point particle to the axis of rotation, but as it rotates it moves and it makes an angle with its original location, theta. So there's two ways that you could describe how far this particle has traveled in a given amount of time. S, an arc length, or theta, an angular displacement. An angular displacement. Okay, so let's keep that in mind, and then let's build a physics of rotational mechanics starting with what we already know. And we could start a lot of different places, but I feel like starting with kinetic energy. So kinetic energy is 1/2 mv squared. It's a scalar quantity. So, even though, strictly speaking here, these are vector quantities, and here S is too, because there's a direction component to it. When it comes to rotation, it's you think about, well, how is direction represented in rotation, or how does rotation have a direction? And it boils down to this: if something is rotating, it could rotate two directions. It could rotate clockwise or counterclockwise, and that's direction. So we're not talking about left, right, up, down. We're talking about a sense of rotation. There's two different flavors of rotation: clockwise or counterclockwise. All right, so S and theta are vector quantities. So let's see here. All right, let's think about V. Okay, so V is in the derivative definition. V, or let's drop all the vector notation and just think of speed. All right, speed is a distance over time. So as a derivative, a definition of as a derivative, it's a derivative of s with respect to time. It's how quickly this arc length is changing. Your position along the circumference is changing. And there is a way to connect s with theta. And I think we would say, well, let's say it like this. If, theta is an angle and it can be measured in degrees, but if theta is in radians, okay, radians, then there's a direct connection between theta and s. And you think about radians, there's 2 pi radians in a circle. You're like, well, that 2 pi, that's connected with the circumference of a circle. The circumference is 2 pi times r. So if you go the whole way around, how many radians have you swept out? 2 pi. What's the actual linear distance that you've traveled? 2 pi r. So the connection between s, the arc length, and theta, the angular displacement, is r. That's what connects it to. So r times theta is equal to s. Let me make that I'll zoom out a little bit. That'll make this r theta equals s. Okay, a linear distance s, an arc length, is the radius multiplied by the angular displacement theta. So if theta is in radians, and you can always write angles in radians if you know them in degrees. There's conversion factors, 2 pi radians and 360 degrees. So you can always go back and forth. So that means if we took the derivative of this expression, a small change in theta is related to a small change in s by the proportionality constant r. dr times theta equals ds. So we can plug in dr and theta in for ds in our expression for velocity, and we get this. Velocity equals r d theta over dt. I just plugged this into just plugging this in up there for ds. So what we have in this is this expression of an infinitesimal rate of change of theta with respect to time, d theta over dt. And that is, think about the units it would have, radians per second. Radians per second. So it's a rate. It's the rate at which radians are being swept out as you're rotating in a circle. So that has a special name. That's called omega. D theta over dt. And that's called angular velocity, or speed in this case, because we're not really considering direction. Or you could call it rotational velocity, I suppose. Angular velocity, and it would have units of radians, rads per second would be its units. So what we have is then, if that we plug that in here, we see there's a relationship between this tangential speed r, the speed of the particle tangent to its circular path, and its angular speed omega, and they're related by r. Okay, so let's write that in up here. Let's put that in up here for v and see what this turns into. So we'll have 1/2 m, and now v is r omega squared. So we get something that looks like 1/2 mr squared omega squared. Okay, so what we have is something that looks like kinetic energy, 1/2 mv squared. Well, now instead of a v squared, we have an omega squared, angular velocity squared, or angular speed squared, and because kinetic energy is a scalar. We have the 1/2, and then instead of mass, we have this thing that looks like mass times r squared. So it's a measure of the mass of the particle, but it takes into account its position relative to the axis of rotation. So it's the mass multiplied by the distance r from the axis of rotation to where the mass is located squared. All right. So let's define that quantity as something called, let's use the symbol I. And we're going to call that, it's got different names. The two that you'll encounter are, this is the one I prefer, rotational inertia. So remember, inertia is this property of an object's ability to resist changes in its motion, to resist accelerations, something with more inertia. And I said, well, inertia is not quite the same thing as mass. Well, in the linear domain, it's a good correspondence. Mass and inertia are related. But in the rotational domain, it's not just the mass that matters, it's also where it's located relative to the axis of rotation. So rotational inertia depends on mass, but it also depends on r squared. It's also called moment of inertia. Okay, so you'll see it written both ways. So when we use this new definition, this new defined quantity, then what we have is the kinetic energy of this rotating particle is 1/2 I omega squared. Okay, so this is rotational kinetic energy. I'll write that KE, rotational kinetic energy. So what we have is the M has become an I and the V has become an omega, but the structure is the same. And so we're going to see this theme played out in many different ways, where in rotational mechanics you'll have physics formulas that look very similar to the ones we've already learned for kinematics, for force, dynamics, force, acceleration, the connection, kinetic energy. But the difference is you'll have rotational quantities or rotational analogs to the physical quantities that substitute in. So instead of M's, you'll see I's. Instead of V's, you'll see omegas. All right, so let's keep going. Well, now let's turn our attention to what happens if this thing isn't moving with constant speed but is being accelerated by some force. Right? There's a force that's exerted on this particle that's causing it to accelerate and spin faster. All right, so let's explore this a little bit. Okay. So we know Newton's second law is net force, but here it's just one force, so I'll just write F equals mass times acceleration. And acceleration is change in velocity with respect to time. It's the derivative of velocity with respect to time. And we just saw that velocity is related to angular velocity with a proportionality constant of r, the radius of the path. So that means if we took the derivative, a small change in velocity would be proportional to a small change in angular velocity. dv equals r dw. All right, that's just this relationship. All right, so we can plug that in here, and what we get is force equals m times r d omega over dt. So what we have is there's a new quantity in here. If omega's angular velocity, the derivative of angular velocity is a rate of change of a rate of change. It's radians per second per second. Let's call that alpha. That's how quickly the angular velocity is changing. That's an acceleration. It's angular acceleration. So we can put that in here. Okay? And so what we have is we have Newton's second law, F equals ma, but now it's starting to look like something different, where now the a was replaced by an angular quantity, alpha, the angular acceleration. And the thing in front of it is no longer mass by itself, but mass times r. And that's starting to look like this, but not quite, because that's mr squared. Rotational inertia is mr squared, so we have mr. But if we multiply both sides by r, we'll get r times f equals mr squared times alpha. That's I times alpha. So we get this correspondence again, where now we have something where the I has taken the place of the m, and then alpha, the rotational correlate to a, has taken the place of a. So an angular acceleration has taken the place of a linear acceleration. Rotational inertia has taken the place of mass, which we can think of as linear inertia. Okay, but now instead of F, we have R times F. So we have a new physical quantity, which depends not only on F, but it's positional as well. It depends on where the force is applied relative to the axis of rotation. So it's how big the force is multiplied by R, the distance from the axis of rotation. And that is torque. Let's go down here. Oops. And it's represented with the Greek letter tau. And it's a little more complicated than just R times F. In general, it's more complicated. But this is a specific situation of a point particle that's accelerating tangent to its path as it goes around in a circle. So let's just write it out like this. So what we have then is R times F is torque equals I times alpha. So we get this equation, which looks very similar to Newton's second law. So let's call this Newton's second law for rotation. So instead of F, we have tau for torque. Instead of m, we have I for rotational inertia. Instead of a, we have alpha for angular acceleration. And of course, I didn't write this out up here, but the units of angular acceleration would be radians per second, or radians per second squared. Okay? All right. So, let's pause for a second. There's a lot of, this may look like a lot of new stuff, but there's actually, the amount of new stuff here is pretty small. It's this connection between linear, or let's call them tangential, physical quantities, the velocity of a particle tangent to its axis of rotation, its acceleration tangent to the axis of rotation, and the angular quantities of angular velocity, which is radians per second, how quickly this thing is sweeping out angles as it rotates in a circle, angular acceleration, angular velocity, and angular displacement. So x's become thetas, or in this case s, because it's not a straight line, it's an arc line. Okay, and v's become omegas, and a's become alphas. So this theme continues, and if we go way back to the beginning of the semester when we were talking about kinematics, descriptions of motion, and that's where we first encountered the quantities of velocity and acceleration and position and displacement, and how they're all connected with each other and with time. And we had this toolbox of kinematic equations. And so now what you can do is, if you're studying something that rotates instead of moving in a straight line, you can take the same equations and just substitute. Anywhere you see an x, put in a theta. Anywhere there's a v, put in an omega. Anywhere there's an a, you can put in an alpha. And problem solve with those same equations in this new regime of rotational mechanics. All right, so how about we do I'll show you how that works one time, and that should be enough to convince you that for any of those kinematic equations of motion, you just substitute the angular quantities for the linear quantities, and you get a tool for studying rotational kinematics. All right, let's do 1. Come over here, get some fresh space here. All right, so the things, let me summarize a few things here. So the relation between arc length and theta is r, but for here, let's just go back, since earlier in the semester we represented distances and displacements with x. Let's write out this relationship like this, that a displacement, could write delta s, is equal to an angular displacement, delta theta, times r, the radius of the path. And then we have v, there we go, r omega, alpha, acceleration equals r times alpha. So, well, maybe I'll erase the deltas for now. But so what I'm trying to tell you is that anytime you find a kinematic equation where there's an x, you can substitute in r theta. Anytime there's a v, you could substitute r omega. Anytime there's an a, you can substitute r alpha. So let's just look at one example. So here's one of your kinematic equations of motion. Okay, x equals x naught plus v naught t plus 1/2 at squared. So wherever there's an x, let's put in r theta. So we have r theta. Actually, before we do that, let's make things simpler on us here. Because I think this is the way it'll be in your textbook. If I subtract x naught from both sides, you get a displacement. A difference in position yields displacement. So that's a delta x is v naught t plus 1/2 a t squared. And then, well, now I gotta, if x equals r theta, delta x equals r delta theta. Okay, so this would become r change in angular position, or angular displacement, and the v naught is an r omega naught. So where there's a v, I put in an r omega. And where there's an a, I put in an r alpha. Okay, so you got the situation where every term has an r in it, and they all cancel, and what you're left with is exactly what I was telling you. So here, this is the original form of that kinematic equation of motion. Yeah, it's written a little differently because I put both x's on the same side. And here's that equation applied to the rotational domain. And you see exactly what I said would happen happened. Everywhere there's an x, there's now a theta. Everywhere there's a v, there's now an omega. And everywhere there was an a, there's now an alpha. Okay, so that same thing will happen to any of the kinematic equations of motion. So instead of, here's another one. V equals v naught plus alpha t. That's going to become omega equals omega naught plus, oh sorry, not, see, I'm already, at becomes alpha t. You have v squared equals v naught squared plus 2 times a delta x. That's going to become omega squared equals initial omega squared plus 2 times alpha delta theta. Okay, so each kinematic equation of motion becomes its same thing, but now with rotational quantities instead of linear quantities. Okay, so believe it or not, I just taught you 70% of all the new material for this unit. Okay, you know there's a problem set. It's be the last one of the semester. I do have one other problem set, but I don't think I'm going to post it. So this problem set is the last problem set of the semester, and we got 2 weeks to work on it. And it explores a host of situations dealing with this new quantity torque, this idea of rotational inertia, rotational kinematics, alphas, omegas, and thetas instead of A's, V's, and X's, rotational kinetic energy. So you think about, you know, one of the, this opens up, it basically doubles the interesting things that we can study in physics when you add this, you know, rotation to your mechanics toolbox. And you know, a good example would be, you know, if I have, we'll think about this because I find it really interesting. If you have like a tire, a wheel that's rolling downhill, it's now moving. So it starts out with gravitational potential energy, and as it rolls down the hill, that gravitational potential energy becomes kinetic energy. Okay, that's a scenario that we studied. But what we'll discover here is, as we just studied it before, we kind of glossed over or ignored and some interesting things that can happen. And so we think about, you know, just a wheel that's rotating as it rolls down the hill. Potential energy becomes kinetic energy, but that kinetic energy is now, there's two kinds. You know, part of that kinetic energy is the old kind that we learned about. Let's call that now translational kinetic energy, 1/2 mv squared. How fast the wheel's center of gravity, center of mass, is traveling linearly through space, 1/2 mv squared. But it's also rotating, so now it also has rotational kinetic energy. So the total mechanical energy is still conserved. The conservation principle can still be used, but now we have two types of kinetic energy to contend with, rotational and translational. Rotational and linear, the 1/2 mv squared and the 1/2 I omega squared. Okay, so we'll stop there for today, and we'll pick this up on Friday. All right, Wednesday, your exam. So I'll post the sign-up sheet. Give me like 5 minutes, and it should be posted. And use the same link on the Sakai website that you used to sign up for recitation. And we won't have recitation on Friday. We'll have a lecture, and we'll do some problem solving. All right. And so sign up to come on Wednesday to take the exam if you want to take it in person. Otherwise, you know the routine. I expect you to have Zoom on a webcam or a cell phone that you can point at your work area while you work, and the ability to take pictures or scan your work so that you can attach it to the problems as you upload them. Okay. I will see you guys later.